Hello, and welcome to 12.2, Stoichiometric Calculations. So now we're actually going to start doing the math behind it. So remember, 12.1 didn't really introduce anything new. It's just redoing stuff that we've learned in previous chapters. Even this isn't really new stuff, we're just putting it in a way that you might not be familiar with. So suppose a chemist needs to obtain a certain amount of product from a reaction. How much reactant must be used? Or suppose a chemist wants to know how much product will form if a certain amount of reactant is used. That's why we use this. So we have, this many grams of the reactants, how much products are we going to get? Well, we can find out based off of stoichiometry. Okay? And instead of reading through this, what we're going to do is we're just going to go ahead and jump into the first little example problem. How can we use this? Well, let's go ahead and look at this. It says, one disadvantage of burning propane is that carbon dioxide is one of the products. The released carbon dioxide increases the growing concentration of CO2 in the atmosphere. How many moles of carbon dioxide are produced when 10 moles of propane are burned in excess oxygen in a gas grill? So it's saying, let's start out with 10 moles of propane. How many moles of carbon dioxide do we end up with? So we're starting with moles of propane, and we're ending with moles of carbon dioxide. So this is what's called a mole-to-mole conversion. And these are the simplest ones. Okay? It says are burned in excess oxygen, meaning we don't have to worry about oxygen. There's enough to continue going. We don't have to worry about running out of oxygen. We need to just be concerned. We start with 10 moles of propane. How many moles of carbon dioxide are going to form from this? Okay? So you're given moles of the reactant propane and moles of the product, carbon dioxide, must be found. The balanced chemical equation must be written. Okay? We need the conversion from moles of propane to moles of CO2. We need to make sure we have the correct mole ratio, because remember, if we don't have if the equation is not balanced, we can't get the mole ratios. So let's go ahead and write that balanced chemical equation. We got CH3 plus O2 because it's burning, right? Yields CO2 and water. Okay? Now, we can balance this using some of the stuff that we learned in chapter, I think, 10, how to balance chemical equations. So, since there's 3 carbon here, we got to put a 3 there to try to match it, but then we have to make sure all of our hydrogens are fine, and we have to put a 4 there, but then we have to make sure our oxygen's fine. So that's a bit of review. Hopefully you guys remember how to do that part. If not, there's a bunch of YouTube videos, or you can bring up that question on Tuesdays or Thursdays in the online meetup or hangouts, whatever it's called. So next, let's determine the mole ratio between CO2 and propane, because that's what we're concerned about, right? Remember, the problem says we have 10 moles of propane. How many moles of carbon dioxide do we get? So we want to find the mole ratio that compares those two things, carbon dioxide and propane. Well, if this is a balanced chemical equation, then for every 3 moles of carbon dioxide, we have 1 mole of propane. So we just put 3 over 1. Okay? So we can multiply that by the known number of moles we have. 10 moles of propane, that's what we're starting with, multiplied by our molar ratio that we found, 3 moles for every 1 mole of C3H8. We see that this cancels out with this. 10 times 3 is 30. So if we have 10 moles of propane, we have 30 moles of CO2. And that makes sense, right? If we have 1 mole of this, we have 3 moles of that. So just multiply everything by 10. If we had 10 moles of this, we should have 30 moles of this. And that's it for mole-to-mole conversion. The only thing we need to do is balance the equation and get the correct mole ratio. That's how you'll have to do this. For number 10, you'll have to balance it. For number 9, I believe it gives you all the reactants and products, so you still have to balance it as well. Yeah. Okay. Now let's look at something called mole-to-mass conversion. So in this problem, it's not just mole-to-mole, we're going from moles to mass. So determine the mass of sodium chloride, or table salt, produced when 1.25 moles of chlorine gas reacts vigorously with sodium. Once again, it's saying that you don't have to worry about how much sodium you have. You have 1.25 moles of gas. How many grams of table salt can you make? Okay, we have 1.25 moles of chlorine gas. That's what we're starting with. And we want to know the mass of sodium chloride that we can make with that. We know this. We do not know the mass. So let's go ahead and set up the equation. We know sodium as a metal is written as Na. We know chlorine as a gas is Cl2. We know that sodium chloride is NaCl. So next we need to balance it. Right? Well, if there's two Cl's here, we need to make this a 2 because there needs to be 2 of those. But that means there's 2 of these now, so we have to put a 2 in front to make 2 sodiums. So now it's all balanced. Well, what are we comparing again? We're comparing what? Chlorine to sodium chloride. So let's find the mole ratio. 2 moles of sodium chloride for every 1 mole of chlorine. Now the question is, how do I know which one goes on top? Why didn't I write 1 mole of chlorine on top of 2 moles of NaCl? Well, we start with what we're given, right? We were given 1.25 moles of chlorine. We want that unit to cancel out, so we have to make sure that however we set up the ratio, this unit is the one right here as well. Oops. This unit is this right here. Okay? So you would put 1 mole of chlorine compared to 2 moles of sodium chloride. 1.25 times 2 is 2.5 moles. If this was a mole-to-mole problem, you'd be done, but it's not. It is a mole to mass. So now we have to go from this to mass. And the way we do that is, everybody said, if you didn't say it, you get an F in this class. Everybody said, if I could hear you, I would give extra credit to those of you who said it. Just kidding. So we multiply the molar mass, multiply NaCl by its molar mass. So 2.5 moles is what we're starting with. Remember, we want the unit on the bottom to cancel, so we put moles of NaCl right here, and we put moles on the bottom. We put its molar mass on the top. All we have to do is multiply 2.5 times 58.44. And we get 146 grams of sodium chloride. This is how you do it step by step, but if this was in class, I would do it this way. Put my given on the top right there, plug in the correct mole ratio, knowing that I need to put moles of chlorine on the bottom, and then plugging in the molar mass value on the very end of it, multiplying everything on the top divided by everything on the bottom that has been multiplied as well, and we get 146 grams. It's the same math, I just like to do it in one step, but the book likes to separate it. You'll get the same answer either way, and either way is correct, it doesn't matter. So that one is mole to mass. Let's do one more. Now let's do mass to mass. So we're kind of adding another step, right? We started out with going from 1 mole of something to another mole of something. Then we did from 1 mole of something to the mass of something else. Now we're starting with the mass of something, ending up with the mass of something else. So we have to go from mass to mole to mass. It's like a whole big 3-step process. So let's look at this. Ammonium nitrate is an important fertilizer. It produces N2O gas and H2O when it decomposes. Determine the mass of water produced from the decomposition of 25.0 grams of ammonium nitrate. Alright? Well, decomposing, you know that means that this thing is breaking up into 2 separate things. It's breaking up into N2O and it's breaking H2O. So when we write it down, we know we're going to have NH4, NO3 on one side, and then the N2O and the H2O on the other. Next, all we need to do is balance it. Excuse me. All we need to do is balance it. So there's 1 nitrogen over here, 2 nitrogens over there. Oh, I'm sorry, there's 2 right here. 1, 2. So nitrogens are balanced. 1 oxygen, 3 oxygen, so that's not balanced. But if we look over here, hydrogen isn't balanced either. But if we put a 2 there, everything works out. So this is our balanced chemical equation. Next up, we have to assume we have 25 grams of ammonium nitrate, because that's what we were given, right? We want to end up with grams over here. So first, if we make this into moles, then we can use a molar ratio to find out how many moles of water we have. Then we can go from moles of water into grams of water just by multiplying the, everybody said? Correct, the molar mass. So let's go ahead and convert ammonium nitrate into moles of ammonium nitrate by multiplying by the molar mass. Now notice this time molar mass, the number is on the bottom because we want to cancel out grams with grams. So grams is on the top, which means we need to throw grams on the bottom right here and put mole on top. That way this cancels out, and it's actually 25 divided by 80.04. And that gets us 0.312 moles. But we're not concerned with moles of ammonium nitrate, we're concerned with moles of water. So let's go ahead and compare moles of water to moles of ammonium nitrate. And we get this conversion factor. Once again, how do I know that this goes on the bottom? Because I want to cancel this unit out, I need to make sure that unit is on the bottom. Right? So this will be 0.312 multiplied by 2 divided by 1, and that gets us 0.624. But we are not done because this is a mass to mass problem. Okay? So we need to go from this moles, finally we need to go from moles into our product, into mass. So we have 0.624 moles of water, and we multiply that by the molar mass of water. Okay? So 0.624 multiplied by 18.02 finally gets us 11.2 grams of H2O. So we start off with 25 grams of ammonium nitrate. The question said, how many grams of water do you end up with? We end up with 11.2 grams. We went from grams of ammonium nitrate to moles of ammonium nitrate to moles of water to grams of water. So it's a whole 3-step process. And if we were in class, I would do it on the board like this, all in one step. You can see what we're given, multiply by the molar mass, paying attention to the fact that I put the grams on the bottom in that second term so I can cancel them, multiplying it by the mole ratio, and then multiplying it by the molar mass of H2O. At that time you see how the molar mass is on top because I want my answer to be in grams. So all the units cancel out except for those grams of H2O. And that's how you do 13 and 14. So this is what we're going to end up with, just like a little visual representation. If you have the mass of a given substance and I'm asking you give me the mass of another substance, you can't, there's no one easy way to do that. There's no direct conversion. You can't skip that. You have to go through this path of going from mass to moles to mass. And these are the conversion factors you're going to need to get there. Excuse me. Over here, if we start with moles, and we just want to end up at moles, this is why those first problems were so easy, because all you have to do is find a conversion factor, a mole ratio. And the last problem was so complicated because we have to use this conversion factor, this, and this. So here are some steps. I did not read these steps, and I'm not going to, but I would definitely read those. It's part of your homework, actually. Right there. And again, if you have any questions, please show up to the Tuesday and Thursday group meetups. I'm also going to post a video that is kind of a review of everything, in case you forgot how moles work or anything like that. A little crash course video. So that'll be in the description below.